Thank you very much. I'd like to thank the organizers very much for the invitation. It's always great to be here in Vienna at ESI. I'm going to talk about joint work with my student Cordelia Tassopoulou. So what we're trying to do here is that we're trying to take effective proofs of classical, well-known uniformization theorems in effective descriptive set theory and present them, in some recursion-free language, right? That's what we're trying to do in an attempt to make the ideas and the proofs accessible to a larger audience. Okay. So just a bit of notation here. We'll have Polish spaces, X and Y. If I don't say anything, if I talk about the light phase point classes, just mean they are recursively presented. Bare space denoted like this, and okay, we have a P which is a subset of X times Y. We have the section, Px is a set of all Y such that Xy is in P, and we have also the projection as a set of all X's for which there is some Y such that Xy is in P, right? Okay. And just for the record, what does it mean to be that P star uniformizes P? It means, first of all, that it's a subset of P, and it's the graph of a function defined on the projection of P. So if we want to make a sketch here, it's kind of pretty easy, I would say. Let's just draw something here. Suppose that this is X, and that this is Y, and then this is P. So the projection here, well, projection X, this set here. Uniformization means that I can find, a line there. This is a P star. Okay, this is the uniformization. Right, and further, if gamma is one of the classical point classes, so this is supposed to be both phase gamma. It's one of the classical point classes in Polish spaces, say open sets, sigma 02, analytic, you name it. We're going to consider sets which are subsets of X times omega. Now, classically, this doesn't make much sense. I mean, especially people in analysis, they're used to seeing sequences, right? Sequence of subsets of X, sorry. Okay, well, this is the same as saying that the corresponding sequence, I mean, you take the section, the set of all X such that Xy is in P is in gamma. Okay, so I'm going to use both of them. Depends. Sometimes I'm going to see the naturals as indexes or as arguments. All right, but it's the same thing. It can be proved for this kind of point classes. Of course, in effective descriptive set theory, it makes huge difference. All right, but classically, there's no difference at all. All right, some uniformization results. Borel set has a Borel uniformization P star, meaning that there is a Borel set P star that uniformizes P under the following hypothesis. So the Lusin-Novikov theorem that we heard before, each section is countable. Each non-empty section is non-meager. This is due to Thomas and Hinman. Each non-empty section has positive measure. This is the Tanaka-Sachs theorem. And each non-empty section is sigma compact, Arseni Kunugi. Okay. So these are all well-known classical theorems in descriptive set theory. So what about effective descriptive set theory? Well, one of the major applications, I would say, of effective descriptive set theory is to give the uniformization in terms of sufficiently definable points. So suppose that gamma is sufficiently good. Here I'm saying it's a spectral point class. Well, I don't want to get into discussion of this. Just take gamma to be pi on 1 and delta to be delta 1, 1. So this is the light phase classes, all right? It works for those. So suppose that I have a set in delta 1, 1. And each section contains a delta 1, 1 X point. Then this thing can be uniformized. Okay, I'm going to mention the theorem in a subsequent slide. But this is kind of a generic theorem for ineffective descriptive set theory that gives us uniformization. So in fact, all the preceding Borel uniformization results can be proved using these methods. Okay, the info on the next slide. And the delta 1, points, on one hand, deliver elegant proofs. Well, that's actually point of view, but if one checks the effective proofs, they will see that actually some of them are shorter, perhaps all of them are shorter, and they all point out to the same thing, the existence of delta 1, points. Okay, so they deliver elegant proofs. But on the other hand, try to explain this to someone who has never heard before recursion theory before. And they will lose you on the spot, right? So it requires, this method requires some non-trivial understanding of recursion theory, okay? So here's the goal. Reformulate the effective proofs in a recursion-free language so that the contemporaries of Lusin would have been able to understand within tools of their era, okay? Take the effective ideas and try to figure out something to rephrase them. Do not use any recursion, do not use anything, just the tools of the era, and present those uniformization results, and try to do this in an elegant way. So I call them hybrid proofs. Okay, and I'm going to demonstrate a few of these proofs to you. So you read well, ineffective delta 1, x points. Whoa, so what is this? Delta 1 x points are it's a highly effective notion. So how are we going to do this? So first of all, suppose that we have a recursive polar space, and I take the x times omega squared. I take a universal set for pi 1, okay, light phase here. So this omega there is the parameter, okay? So I have a universal pi 1, subset of this, parameters there on omega. I uniformize it by some g star in the last variable, and then the remark is that a point in the Borel space is delta 1 in x, if and only if for some point I, this I, the code, the graph of alpha is actually this GIX section of the uniformizing set. Essentially, what I'm telling you here is that function f, function alpha, say, omega to omega, is delta 1 x recursive. So I don't know, you can see here very well. Let me try it. So I'm just telling you that this is, let's say simpler, delta 1 recursive, if and only if its graph is pi 1. Now this may sound strange because we know the thing about the sigma 1 graphs, but the thing is that this alpha is polar and takes values in omega. So you can actually rephrase the whole thing. If and only if, for all k, if nk happens to be in the graph of alpha, then this k has to be the m. So if the graph is pi 1, well, this is a sigma 1 condition on the graph. Okay, again, right? You can reformulate this, and the reason you can do this is because this k takes values in omega. If it was like a recursive polar space Y, you wouldn't be able to do that. This would be co-analytic. Okay. So that's the remark. So what we're trying here to do is that, okay, forget about the universal set and replace the GI section with some HI section. And this HI should be HI star, meaning that it's uniformized in the last variable, meaning that it contains at most 1 point. Okay, the section, if it's not empty, contains exactly 1 point. So we call this kind of sequences, well, X-admissible. Okay, it's just a term. I'm open to any suggestions for a better name there. So, okay, an X-admissible sequence is a sequence of subsets of X times omega squared, which is uniformized in the last variable. If I have sequence like this, I call the alpha in the Borel space an HX point if there exists some I such that this condition holds. So essentially, it's the thing above. Now, so for each HX point, there is so some I. I'm going to call this the code of alpha. Okay. The important thing is that this alpha n is unique. There's no because those sets are uniformized in the last variable. So the H there is just to, refers to hybrid arithmetical, delta 1, 1, or if you like, hybrids. Okay, it's the same thing here in this context. All right, so how to build these points? Well, there is this uniformization theorem by Kreisel. I have P subset of X times omega, which is pi 1, 1, coanalytic. Then it has a coanalytic uniformization P star. Now, this is a special case of a theorem of Kondo. Instead of omega, we have Polish spaces. But as I said, we want to do things as basically as possible. Okay. So we're only going to need here omega. And it's hard to overstate the importance of Kreisel uniformization in effective descriptive set theory. So just for the record, I'm just going to say here a quick proof. Just have Borel function such that for all xn, f of xn is a linear order and xn is in the set if and only if f of xn is a well order. Okay. The idea is to define the uniformization as follows. Xn is in P star if and only if, first of all, f of xn is a well order. So I'll be in P after all. F of xn has the least order type among all others fxm's for m being in the px section. So you pick the least order type. And once you pick the least order type, then pick the least natural n where this order type is achieved. So that's the idea. The least order type and then the least natural where this is achieved. So it's clear that this is a uniformization. The thing is to prove that it's coanalytic, right? Because, I mean, this kind of conditions there, the least order type and so on, okay, it needs some consideration. But the important remark here is that if xn is a well order, then I claim that actually, you know, for example, the second condition being the least order, this holds if and only if for all m there is no embedding from f of xm into an initial segment of f of xn. So why is that? Well, suppose that this is where not true, then since f of xn is a well order, then f of xm would be a well order, so we would be in P. And since we would be in P, we would find something below, which is contradiction. And the other way around, if this is not the minimum, then I can certainly find some xm in P, such that, well, this is violated. I can find, you know, strictly below, and I can find a well order, an embedding there. So the last thing here, the last condition, is actually coanalytic. So I can rephrase this second condition in a coanalytic way, and I can do the same for the third condition with similar argument. So after all, this P star is actually coanalytic. So it's actually a pretty basic idea here. How to prove uniformization, no Kondo theorem, nothing. So just some basic tools there, playing with the well orders. Okay, so some basic results is the theorem of restrictive quantification in effective theory. If I have a pi 1, 1 set, and I take the set of all x's for which there's actually a hype in x witness, that's what I mean there, this is also pi 1, 1. So I'm going to rephrase this now in terms of classical theorem. So it's the hybrid theorem. Okay, so we will replace delta 1, 1 x with h of x points. So suppose that x is a polar space and q is a subset of x times n, such that for some admissible sequence, so these are, sorry, the delta 1, 1 x point, if q of x is not empty, then it contains an hx point. So I'm not going to worry when I have an hx point. I'm just saying, okay, whenever it's not empty, just suppose that you have an hx point. Then the following holds. If q is coanalytic, then the projection is coanalytic, and as a consequence, if q is Borel, well, the projection is analytic and also coanalytic, so it has to be Borel. Here's the proof. 3 lines. That's the proof, using the hx points. So what does it say there? So the first line there, it's, okay, let's analyze this thing. It says, well, actually, I can find an hx point with code I. For all n, there is m. This m has to be unique, so I can define, let me make some space here. I don't think we need this any longer. Alpha n is the unique m such that for all n, n m is in hi star. Okay, so I get the hx point. And the next two lines, it's actually where the party begins. Let's check the third one. What does it say? Well, suppose that we have some beta there. This thing says that this beta cannot be the point that you have there, cannot be this alpha. So these two lines say that, you know, for all beta, you're either in or you cannot be the alpha that you've chosen. Well, apply this for beta being the alpha that you've chosen, so this thing is false, so you have to be in. So this is how you enforce being the witness there being in Q. This line here. It's actually co-analytic condition, as you can see. So I explained to you how we can get from here to the left. And the converse direction is actually the hypothesis. If Qx is not empty, I can find an hx point. So this is the whole thing. So that's the proof. Let's see a quick application. The set of unicity points of a Borel set. So it's the set of all, suppose I have a B subset of x times y, it's Borel. Then the set of all x's for which there, well, R is a set of all x's for which there exists a unique y, such that x, y is in B. This is co-analytic. Let's see how we can prove this. First of all, we may assume that Y is the Borel space because it's the continuous surjective image of a Borel set. Okay, closed set actually. But if you want to be quick, if you make it G delta, that's fine. It works. Okay. So we may assume that Y is the Borel space. I define this Q. Well, this Q says, okay, if B of x is not empty, then it has to contain a unique point. That's the whole thing here. For all beta, if x beta is in B, well, this beta has to be this alpha there. Of course, it could be that B of x is empty, in which case all alphas go in there, but that's okay. The important point thing is that Q is co-analytic and its projection is R. So I'm going to apply the preceding theorem and show you that actually this Q satisfies the condition. If Qx is not empty, it contains an hx point. So which hx should do, which h should we get? Well, here's the thing. Take h to be the set of all x and m that satisfies this condition. For all beta, if x beta is in Q, then at n, this beta should take the value m. Of course, this thing could have many m's if Q of x is empty, but if it's not empty, well, it will have only one thing, okay. But since we don't know that it's always unique, then we uniformize it using Kreisel uniformization, and then voila, take hi star to be this h star. It's actually the same index of the computation there. And this is done, and this is all, okay. If Qx is not empty, then it contains a point like this, and therefore from the preceding theorem, this thing is co-analytic. So that's an application, right? Okay. A very quick proof of Lusin's theorem. Now let's check the other thing there. It's a delta uniformization theorem. If Q is subset of x times n is delta 1, 1, and each non-empty section contains delta 1, 1 x point, well, then the projection is delta 1, 1. Well, actually, we proved it there, the classical version. And Q can be uniformized by delta 1, 1 set. Let's see the hybrid version of this theorem. Suppose, again, Q is as before, now is Borel, and that for some x admissible sequence, every non-empty section contains an hx point. Okay. Then Q is uniformized by a Borel set. Now, the proof of this is somewhat longer, but not very different from the preceding. First of all, I'm going to take the set of codes for x. So xi is in D. If first of all, again, I have an hx point. And the second thing is the same as before, but now the argument is I, is not alpha. Just says, okay, for all alpha, I'm either in there or I'm not the high x point that I've chosen, that I've defined before. Okay. And then, of course, I could have many i's. I mean, Q of Qx, if non-empty, it could contain a lot of hx points. So I need to pick one. So I uniformize it in the last variable using, again, Kreisel uniformization. And then this meaning of Q star is actually take the alpha for which I have this thing for the I that is uniformized there. All of these things are co-analytic conditions, okay? And then, well, we wanted to have Borel Q star. Well, actually, I mean, this Q star is the graph of a Borel function. So we do, again, the same trick. We show that it's also analytic, and hence Borel, because it satisfies this equivalence. So it's in X alpha is in Q star, if first of all it's in Q, and satisfies this condition. Now, this thing here, it just says, okay, if you give me some other beta, which happens to be defined like Q, then beta of n has to be alpha of n for all n. I can just rephrase it using arithmetical quantifiers because of this uniqueness stuff. Okay, so this thing says, you know, this beta has to, this m has to be the alpha of n for the alpha that is defined. That's essentially, I mean, it's easy to check these things. And this is the uniformization that we want. And let's mention now a third theorem. We're going to apply both of these things, delta uniformization and effective Borel. If P is light phase sigma 1, 1, x and contains a non-delta x point, so a point which is not in delta 1, 1 of x, then contains an uncountable set. Okay, this is stronger than the perfect set theorem. Perfect set theorem says that if you have an uncountable analytic set, then it contains a perfect subset. Well, if P contains a point not in delta 1, 1, well, all right, well, cannot be countable, right? Yeah. Well, let's see what's stronger. Right, so suppose that, or, well, okay, let me rephrase it. If you start with an uncountable sigma 1, 1 x set, then it cannot be, cannot consist of delta 1, 1 x points because it would be countable. Okay, so it has a point not in delta 1, 1, and therefore it contains an uncountable set. Okay, let's rephrase this thing. A hybrid version. For every analytic P subset x times bare, there exists an x-admissible sequence such that for all x, either P of x contains a perfect subset or Px consists of hx points, consists of delta 1, 1 x points. I'm going to prove this to you classically. But before we do this, let me just mention two corollaries. First one is the Lusin-Novikov theorem. If P is Borel and each section is a countable set, then P admits a Borel uniformization. Let's prove this. Actually, the proof is on this slide. Well, first of all, we may assume that Y is the bare space, as usual. And let H be as in the hybrid perfect set theorem. Okay. Well, each non-empty section contains an hx point. Well, in fact, it consists of hx points, right? Because of, it cannot be, otherwise it would contain a perfect subset, but P of x is a countable set. Okay, so from the hybrid Borel uniformization criterion, the theorem that we proved before, it admits a Borel uniformization. That's it. That's the proof of Lusin-Novikov theorem using these high hx points. It's the effective proof. There's nothing really new here. It's just, you know, more delicate computations, but using a classical notion, hx points, the ineffective delta 1, 1 x theorems. Okay, let's mention the other corollaries, again, Lusin-Novikov, under the same assumptions as before. So P of x is countable. Then I can actually write the Borel set as the countable union of Borel graphs. Okay? That, I mean, Borel sets that uniformize P. Each of them uniformizes P. Now, the proof of this is a little bit longer, but it's still an application of the effective perfect set theorem and the things that we mentioned before. Suppose that we have, well, we may assume that Y is the bare space. Let H be as in the hybrid perfect set theorem. Well, P is Borel, so in particular it's analytic. And that each non-empty Px consists of hx points. So we're going to use it. So first of all, we do the same trick again. I just put I here at the beginning for some reason. We are in P, and this alpha, it's actually the hx point that belongs in the section Px. All Px consists of hx points. Okay? So essentially, I'm picking, I'm just saying that alpha is the hx point with code I. This is co-analytic, and then I uniformize it in the first variable. Okay, so essentially for all x and alpha, I pick one code. This is what I'm doing there. Okay, and actually, well, this is a graph of a delta 1 measurable function, the recursive function. So it has to be analytic, and it's the same trick as before, as the one thing that I raised. I mean, this thing, if I don't leave, I mean, this Q star, if I don't leave X alpha is in P, and for all J, if Jx alpha happens to be in this graph, then J has to be I. Okay, this is an analytic condition. So at the end, this Q star is actually Borel. Okay, so I uniformized it by Borel set. Q doesn't have to be Borel, but the uniformization is actually Borel. So we know that for all x in alpha, there is some I such that this thing happens, which means that alpha, that I is the code of this alpha, because P of x consists of hx points. So from the property of the uniformization, for all x alpha in P, there is also some I, unique I, such that Ix alpha is in Q star. Okay? All right. Further, this section, Q star Ix, now the alpha is in the last variable, contains an hx point. In fact, it consists of the unique point alpha, which is encoded by this I. Okay? So from the hybrid theorem, the restricted quantification, its projection has to be Borel. Each empty section has it's an hx point, so its projection has to be Borel. Well, let's take now the Borel P star, a P prime that uniformizes P, and define P star I like this. X alpha is in the P star I, first of all, is in P. Here's what happens here. Either alpha is the hx point encoded by I, just in case this Ix alpha is in Q star, if this I is the one that we have chosen before, or you know what, this Qix, the projection of this Q star is empty. Well, Ix is not in the projection, so no alpha can be achieved. And in this case, well, I just need to plug in something. Well, alpha is the thing that is uniformized. So that's the idea behind this. So it's actually, I'm saying either alpha I is the code of alpha, the unique code of alpha that I chose before, or I have no codes there, but because I need to put something there, because I need to define this for all i's, well, just pick the thing that you uniformized before. Now, this is a Borel set. P is Borel, Q star is Borel, projection is Borel, everything here is Borel. This works. Okay. So these are the P star i's that we have in the Illusion-Novikov theorem. Okay. So you see, it's kind of very simple to define. You just sit down and verify the properties. And let me just say a few things about, I think I have like 10 minutes or something. A few words about the proof of the hybrid perfect set theorem. Okay, so just perhaps go a little bit to remind you of what this is. For every analytic set, we need to find an x admissible sequence such that for all x, either P of x contains a perfect subset of P of x, or P of x consists of hx points. Okay. So let's try to prove it. First of all, let's make a very brief review of the Mansfield's proof of the effective perfect set theorem. We start with the sigma 1 x point, and we have a tree representation. Alpha is in P if and only if, well, P is a subset of the Baire space. Just keep it simple, right? If and only if there exists beta such that the pair alpha beta is in the body of T of x. Now, usually we can get this done with recursive Tx, well, recursive in x. But I want the tree to be pruned, meaning that for all, well, it's a tree of pairs, meaning that for all uv in 3, well, this should be t of x right there. It's a typo. If I'm in there, then actually I can find an infinite branch extending this thing, okay? So to get this thing, I need to prune the tree, so I end up with a sigma 1, 1, 3. Oh, that's fine. Okay. So if for some uv the projection is a singleton, say singleton alpha 0, then this alpha 0 satisfies this condition there. Simply says, you know, if I have some alpha beta in there, then this alpha is actually alpha 0. This is what it says, this line. Okay. This is pi 1, 1 condition. And since a pi 1, 1 condition, it's a singleton, well, okay, bad formulation. It's a pi 1, 1 condition, means that the graph of this alpha 0 is pi 1, 1. So it follows easily that alpha 0 is a delta 1, 1 x point. Follows very easy, just the way I explained before. So the idea in the effective perfect set theorem is that if we throw all delta 1, 1 x points out of P, so the set of delta 1, 1 x points is actually pi 1, 1 in x, throw them out, so we will end up still with a sigma 1, 1 x subset of P prime. It's not empty because it contains P that we started with contains points not in delta 1, 1. Okay, so we throw them all out, still not empty, it's sigma 1, 1 in x. Then we represent it again with a tree, call it Sx, and then for all uv in x, the projection has exactly 2 points. Why does this happen? Because we threw out all delta 1, 1 points. If it had 1 point, then it would satisfy something like this. Okay. The S of x will still be sigma 1 x. And then, using this thing, we can build a perfect subset. That's Mansfield's idea. It's Mansfield's proof, okay? Let's see how we can do this here. Toward a hybrid proof. So we do the same thing again. We do this uniformly on x. And what does it mean now to be uniformly? It means that if I take the set of all triples, x, u, and v, such that uv is in t of x, it's analytic. And t of x is a tree. Okay, we can do this stuff. This is easy representations of analytic sets. The preceding star, let's say it's a unique branch, suggests to define this HUV, X and M is in HUV, such that for all alpha, if alpha and beta, if they happen to be in this, if it's an infinite branch, this alpha of n is the M. M is the alpha 0 on n, so the unique thing that we're going to have. But here is the problem now. I mean, okay, we can uniformize it again and then get a, an admissible sequence. So actually, the indexes there are the pairs in the tree. So as the effective proof, we would like to remove the h of x points, okay, so that the projection will have 2 points, right? And start over with a new tree representation. However, if you remove specifically these points, well, you need to redefine the new analytic set that you've got, right? So forget about t, you're gonna need some new s there. And if you have some new s, then you're going to end up with a new sequence, h prime I call, and you have a problem, right? So because you need to remove new points, and then you need to repeat the process again and again. So it looks like a catch-22, I guess, forever catching train. But guess what? We can fix this, well, using methods of recursion theory, but okay. I'll into the moment. So the preceding is the price to pay for abandoning the class delta 1 on x in favor of hx. Delta 1 of x has closure properties, right? It has some serious closure properties. This h of x that I defined is just for this specific instance of a pi 1, 1 set. Okay, what's going on there? Fortunately, the spirit of cleaning helps us, okay? Famous non-recursion theorists. There's this cleaning recursion theorem, which we could actually say as a fixed point theorem. So it's the recursion theorem for relations. Consider the standard universal sets. So this is a universal set for sigma 0, 1, and this is for pi 1, 1. Okay. Then every pi 1, 1 subset of n times x satisfies actually this property. There is some epsilon 0 such that the epsilon 0 of this p is the epsilon 0 of g. Okay. This can be proved classically. Believe me, if you gave me 5 minutes on the blackboard, I could just prove it to you. Okay, clearly, of course, prove it for the light phase point classes, but his arguments go through just as good in the classical case. It depends, I mean, it uses the fact that this universal system is actually good. We have this continuous function S that comes from the SMN theorem. But since we're in the bare space and we worry about classical stuff, it can be proved very easily. Okay, so going back to the hybrid proof, so don't be scared, okay, we're really close to finish. So we have the space X. This thing looks a bit intimidating, but it's actually this U and V that we got there. And this is the N and M that come, from the graph of the function alpha that we have there. So we start with a universal set for pi 1, 1, actually the preceding universal set. And now we define epsilon x alpha to be in Q if, first of all, I am in P. This is the analytic set that I start with. And here's the line there. So essentially, what we're trying to do, we are removing the points that will show up as the things using this pi 1, 1 condition. Still, the thing is that we don't know yet which points we're going to remove, hence the epsilon. Okay. The meaning of the above is to pretend that we have removed from P of x the point of edge x points, and these points still don't know them yet, but they will show up as the for some fixed epsilon 0 that will come from the recursion theorem. So what we're going to do here, okay, the set Q is analytic. I give it a tree representation using these sigma 1, 1 conditions and stuff, okay, and then we call the double star thing. Again, I'm the unique infinite branch in this subtree there, okay. So I'm going to repeat the definition, but now I'm going to plug in the epsilon there. The epsilon is it's from the tree representation, because now Q has epsilon as an argument. I have this thing there. Pi 1, 1 condition. I uniformize it in the last variable, try the uniformization, and I apply the clean recursion theorem to get some epsilon 0 such that this works, this holds, okay? And guess what? Now I'm going to define the H star UVs is a set of all triples there, such that this happens for this H star that uniformizes H. But guess what? This is now the same as a set of all triples such that I am in this G. So I do not uniformize G, I uniformize the H. But it's the epsilon 0 section of G. So what we have achieved here is the following. If we define P prime to be the epsilon 0 of this Q, then, well, you recall the Q there, this Q, I'm in P, and I removed these points that come out of G. If I plug in here epsilon 0, then actually, I removed the H points. And still I have the tree representation. So essentially what I managed to do is to remove, at the beginning, the proofs, the points that I need to remove. Clean recursion theorem makes this possible. Okay, so again, if this were a singleton, then I would have this thing with H star, and it would contradict this thing here. I removed the things that I need to remove. Okay, so the projection has at least 2 points, and then I can build the perfect set the usual way. So overall, no more slides. This is the last one. So overall, what we did is essentially reformulated this whole thing in a recursion-free language. Sometimes we can get through using just these basic computations, like the set of unicity points. Some other times, like the hybrid perfect set theorem, we need to do a little bit of recursion, still formulated in classical way. And, all these things can be understood easily by a beginner in descriptive set theory. They don't need to get into this recursion-theoretic language, just understand basic representations of analytic sets, well orders and stuff, and then you've got all these theorems. Okay? So this is an attempt to make these ideas and proofs accessible to a wider audience. I'm not really talking about beginners in descriptive set theory. I'm talking about people who have some interest. They work possibly in analysis or algebra and stuff, and they want to hear about this stuff, well, this is the proof, this is the idea. Okay? Thank you very much for your attention.